Let's first talk about some graphs for one quantitative variable. You know, we're kind of following this little outline. We started with one categorical variable. We talked about graphs, summary, statistics. Then we talked about two categorical variables. We talked about graphs, summary, statistics. Now we're talking about one quantitative variable. And we're going to start by looking at graphs. And in this section, there's two basic graphs that we're going to talk about for one quantitative variable. We're going to add a third graph in section 2.4. First two graphs we're going to talk about, one is called a dot plot. So the first one is called a dot plot. And a dot plot is a pretty basic form of graph. So if you remember when we did that Princess Bride activity and we were choosing the words from the Princess Bride, and then I had all of you use your annotate tool to put little stars on the graph, that was essentially a dot plot. So a dot plot along the x-axis, then we have a number line. So the x-axis is a number line. And then each dot on the graph, it represents a case. So just like the one that we did in class, each star on that graph represented a case. So each dot represents a case. And if two cases have the same value, then we just keep stacking them on top of each other. So if two cases have the same value, stack the dots. So dot plot is a very basic graph. It's easy to construct by hand, which makes it kind of handy dandy. So we're going to go ahead and look at doing a dot plot. So to help me out, if your last name starts with M through Z, so M through Z, then tell me how many pets you have. You can type that in the chat window. Here's the data we just collected from all of you. So if I want to do a dot plot, then I first just create my number line. My number line is like a ruler, like looking at graph paper, something like that. And I just need to make sure that it goes from the lowest number to the highest number at least. So in this case, I want to make sure it goes at least from 0 up to 8 with evenly spaced tick marks. So I'm going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll write that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so then I'm just going to look at my values and I'm going to plot them with a dot. Now, my computer pen really does not like dots. It thinks I'm trying to do something else when I try to do a dot. So I'm going to put a little X instead of a dot, which is fine. But, you know, a true dot plot, of course, would have real dots. So my first value is 2. So I'm going to put my dot / X right here at 2. Then I have 3 ones there. So I'm going to have 1. And there's, because it's the same value, I'm just going to stack them on top of each other like this. Then I've got another 2. Then I have a 4, then I have a 6, and a 0, then an 8, and another 2, and then 2 more zeros, and a 6, another 6. All right, so this would be an example of a dot plot for this data here. And we're going to talk about the other graph first, and then we're going to talk about what we're looking for, because it's actually the same on both of these first two graphs that we're looking at. Okay, the second graph that we have for quantitative data is called a histogram. Okay, a histogram is similar to a dot plot in that it's going to help us see the distribution of a quantitative variable, but it's a little bit more structured. I don't know if that's the right word for it. The x-axis on a histogram is a number line, just like it is with a dot plot. The y-axis, so there is a y-axis on a histogram, and the y-axis is going to be frequency. So on our histogram is going to have bars, and the bars are going to represent the data. And how we figure out how to draw these bars is first we have to create these things called bins, or StatKey calls them buckets. But basically a bin or a bucket, it's a range of data. And like when I hear the word bins, like it just makes me think of toys and cleaning up toys, because you know, I have 7 kids, so we have a lot of toys, and we have a bin for the Legos, and we have a bin for the trains, and we have a bin for the dishes, and a bin for the dress-up clothes, and all that stuff. And basically, when we're making a histogram, it's a similar thing. We're going to create these bins. The bins are just ranges of data. So it might be like 0 to 2, and then 2 to 4, and 4 to 6, and 6 to 8, and 8 to 10, something like that. And then we're going to count how many observations fall in each bin. So we're really just like cleaning up the toy room. Okay, we're just sorting all the observations into their appropriate bin. So I'll write some of that down. So we're going to create bins. Okay, and then in parentheses, I'm going to put or buckets, because buckets is what it's called on StatKey. Okay, and these bins or buckets, they're just ranges of data, which is ranges of data. Okay, and then we're going to count how many observations or how many cases fall in each bin. So we're going to count how many cases fall in each bin. Then we're going to create our graph. We're going to draw a bar. The sides of the bar are going to be determined by the upper and lower bound of the bin, and the height of the bar is going to correspond to frequency. So bars go from the lower end of the lower end to the higher end. And end of the bin, I should say. Let me go back and fix that. They go from the lower end of the bin to the higher end, and they have a height equal to the frequency. Okay, the frequency is just the count of the number of observations that fell in that bin. Now, it is totally possible to do one of these by hand. But as you can see, it's not going to be quite as simple as just creating a dot plot. A dot plot is pretty simple to create by hand. A histogram takes a little bit more work to create by hand. So pretty much in our class, we're going to use StatKey to create our histograms. And the most important thing about the histograms, as far as I'm concerned, is I want you to be able to interpret the histogram and understand what it means. So I am going to show you inside of StatKey where we can access the histograms. And you guys are going to be creating a histogram as part of your written homework this week. And so this will be good for you to see here. So the easiest way to access StatKey is really just to Google StatKey. So that's what I'm going to do. So you literally just go to Google and you type in StatKey. And if you want to do this right now on your own computer to make sure you can do it, that's totally fine. So when you do that, then the very first thing that comes up is StatKey Lot 5. That's the option that we're choosing. So Lot 5, that's the authors of your textbook. There's 5 members of the Locke family that created your textbook. So they created StatKey as a way to do basically all the analysis that we're going to need to do in our class. So this is going to be a really helpful tool for our class. It's not super powerful beyond our class information as far as statistics goes, but it's great for the stuff that we're doing in our class. So here's what StatKey looks like, and it's nicely organized in here. I like that about it. This whole left side over here where it says descriptive statistics and graphs is where we're going to be for all of chapter 2. And as long as you can identify what situation you have, like if you have 2 categorical variables or 1 quantitative variable, then you're going to get to the right place. So for example, we're going to go here to 1 quantitative variable first of all, and we get all these different options. So first of all, because this is made by the authors of your textbook, then one great thing about that is that they have preloaded several of the data sets from the homework and things and the exercises in here. And you can figure out if your data set that you need is preloaded by clicking on this drop-down box over here on the upper left-hand corner. So these are all the data sets that are already preloaded in here. By preloaded, I mean all you have to do is like click on that data set and the data is already there. Like you didn't have to upload it in there. You didn't have to enter it yourself. So it's super handy dandy. If the data set that you want is not in here, then you will have to upload it from the course data website. And I don't think that you're going to have that issue with any of the problems this week in the homework that I assigned, but you might have it next week. So I do have a video that shows you how to do that when you get to that point. You can also enter your own data. So if I just click on edit data here, I can delete all the information that's currently in there, and I can put in my own data. So we were looking at pets. So I'm going to enter in all that pet data that we just collected. So we had 2111246082006. All right, I didn't have an identifier. I didn't write down people's names that went along with it. So I'm going to uncheck that first box. But I do have a header row because I called it pets. So then I would click on OK. All right, first off, it's going to show me a dot plot of my data, which should look just like the dot plot essentially that we drew together a second ago. And then notice up here there's other options. So there's this option for histogram. So I can go ahead and click on histogram over here and it will draw the histogram for me. Okay, now you notice over here on the right side, there's this histogram controls button, okay? And here you can use this slider bar to change what the bucket size is, basically, okay? So you tell it how many buckets you want and it's gonna adjust the graph based on how many buckets that you're having. So you can see that the overall pattern of the points tends to stay the same no matter how many buckets that you have in general. But depending on your data, you know, I think it automatically chooses 10 buckets for you on any given graph. But sometimes, depending on your data, it might be more interesting or look better with a different number. So you can kind of use the slider bar to get your graph so that it looks good. And by looks good, we just want to be able to identify 3 things on our histogram. And same with the dot plot, which we're going to talk about. We're going to look for shape, center, and spread. So we're looking for 3 basic things, as I mentioned before. Okay, I'm going to talk about all 3 right here, and then I'm going to show some examples, and we're going to look at some things together. But we'll write them all down first, and then we'll look at the examples. So the first thing we're looking for is shape. Okay, shape is the overall pattern of the points. All right, and there's some very common ones that we're looking for, some common shapes. So there's symmetric, there's skewed. If we have skewed, then we're looking at right skewed, left skewed. We're going to look and see if there's multiple peaks, which we call modes. So that's going to be interesting. Those are kind of the basic ones that we're looking for. Skewed right, skewed left. We're going to look at number of modes, which is just the number of peaks. Okay, and kind of going along with shape, we're also going to be observant of whether or not there's any outliers. Okay, so I'm going to call this like 1A because it kind of goes along with shape, but we are going to be looking for outliers. Okay, and outliers are just points that are noticeably different from the other data values. So outliers are observed values that are notably different from the other data values. All right, so if we have a skewed distribution, we're typically going to see outliers in that distribution. Okay, the second thing we're looking for is the center. Okay, and by the center, we want to know where's the middle or what's a typical value for this distribution. And then the third thing we're looking for is spread. And for that, we want to know how spread out is the data, how much variation is there in the data set. So how spread out is the data, or how much variation is there? All right, so we have these like 3.5 things that we're looking for. Some people like using the acronym SOX to remember, okay, if I'm looking at a dot plot or a histogram, I have to look for SOX. And SOX would stand for shape, outlier, center, and spread. So if you like acronyms, then you might like the SOX acronym to help you remember what to look for on a dot plot or a histogram. Just a couple of examples of a dot plot versus a histogram. This is data, it's the world gross for movies that were made in 2011 from Hollywood. So if you remember, anybody remember any movies back from 2011? Here's actually part of the data set that you can see here. So maybe you might recognize some of the movies that came out back in 2011, 9 years ago. Okay, so here's a dot plot of that movie data. So the world gross, that's like how much money that they made. And you can see that most movies made between $0 and $200 million. And then a few movies made a bunch of money. And these 3 movies out here made like a ton of money. So lots and lots more than everybody else. So this is an example of a dot plot. Remember, each dot in a dot plot represents a case, which in this case, a case was a movie. So each dot represents one of the movies that was made in 2011, or that was released in 2011. All right, and here is a histogram of the same data. So you can see that it's similar in appearance to the dot plot, only now we're going to have the bars. We see the same kind of thing. We can see that, like, hey, tons of movies made between 0 and 200,000 here, and then a few movies made a little bit more than that. And this histogram is a little bit better than the one that I was showing you on StatKey. Kind of gives us a better idea of what we're looking for here. So the sides of the bar here represent the upper and lower bounds of the bin. So these guys, when they made this histogram, it was done, their bins went from 0 to 200, 200 to 400, 400 to 600, 600 to 800, 800 to 1,000, you know, etc. So their bin width was 200. And then if I look at the height of the bars, it tells me how many movies fell in that bin. So for the first one, 0 to 200, it looks like about maybe 110 movies or slightly less, 108 movies or so fell into that first range of 0 to $200 million. If I look at 200 to 400 and I follow the height of that bar over, I would guess probably 12, 13-ish movies made between 200 and 400 million dollars. The next bar looks like maybe 7 or 8 movies made between 400 and 600 million dollars. So that's kind of how we read our histogram. We can identify how many cases fell in each of those groups. Thinking about our shape, here's 3 different histograms that we're looking at here. Okay, one characteristic we're looking for is symmetry. Okay, and if something is symmetric, then if you draw a line down the middle, oh yeah, sorry, now I'm seeing stuff over in the chat window. The y-axis on histograms is frequency. Yeah, it's a count. Thanks for the people that answered for me. So we're looking at whether or not something's symmetric. If it's symmetric, then if I draw a line down the middle, then it's roughly a mirror image on both sides. It doesn't have to be a perfect mirror image. We're just looking for like roughly symmetric when we call something symmetric here. So this first one here with the sleep, number of hours of sleep data, then this one is pretty symmetric. Okay, this next one here for hours of exercise in a week, this one would be skewed to the right. Okay, so it's skewed when it's obviously not symmetric, so I can't draw a line down the middle and have it be the same. And we typically have a long tail out to one side in a skewed distribution, like we do here for this one. So whatever side the tail is on is where how we determine the skewedness. So the tail is on the right side, so this one is going to be skewed right. And then the opposite way is what we have over here. If the tail is on the left side, like it is here, then this one's going to be a left skewed distribution. So it's kind of leaning that way. So this is just a memory trick that I use to help me figure out right skewed versus left skewed, because back when I took this class, like 20 plus years ago, then for some reason it just always befuddled me. Like it wasn't instinctive to me which was right skewed and which was left skewed. So when I was a student just like you, this is the memory trick that I came up with, and it has never failed me. So I thought I'd share it with you. It's a little bit goofy though, so if you don't like it, then you don't have to use it. Hi class. Back when I was a student taking this class in college, I used to get really confused between the difference between left skewed and right skewed when we were talking about the shape of a histogram. So I made up this really silly memory trick to help me remember, and I thought I would share it with you. And it is really goofy, so if you like it, great, and if you don't like it, then pretend I never showed you. So here I have two different histograms, and you can see that they're both skewed histograms, and my tendency is to look at where all the big bulk of the data is and think, oh, you know, that's what I want to call the skewedness. I want to call this left skewed, but it's not. The skewness goes with the tail right here. So this is how I remember that. I try to make my arm look like the histogram. So for this one here, I would take my hand like I'm going to cup it, make here where the big tall part of the histogram is, and my arm is going to be the long tail of the histogram. So once I've made my arm look like the histogram, what arm am I using? Right arm, which means this one is right skewed. Now if you look at this other graph over here, I can do the same thing. Again, my goal is just to make my arm look like the histogram. So in this case, my hand is going to form the cupping shape. That's going to be the big tall part of the histogram. My arm is going to be the long tail of the histogram. And if I look at which arm I'm using my left arm. Therefore, this histogram is left skewed. So I hope that you find this tip helpful, and have a great day. All right, so hopefully that'll help at least one of you out there, then it'll be worth showing to everybody. And I always think it's funny when I give like a in-person test or something, I can see people on the exam like holding their arm down low, kind of doing the histogram dance, trying to figure out right skewed versus left skewed. But like I said, it has never failed me. So even though it's goofy, I like that trick. Okay, so next let's talk about the center, okay, of the distributions. When we're talking about center, we mentioned that it's a typical value or kind of the middle of the distribution. So there's two kinds of ways that I look at how to find center using a histogram. And keep in mind that even later on in our class period, we're going to talk about how to do some actual calculations for measures of center. But right now, we first look at the graph and we're getting a feel for the data in the graph. And so we're just trying to get a feel for what the center is. So we're estimating, we're eyeballing it. So these are the two methods that I use. So one method is I try to imagine that my histogram is made out of solid material, like maybe I've built my histogram out of Legos or something like that. And if my histogram was made out of solid material, is made out of Legos, then if I could put a little point somewhere and have the histogram be perfectly balanced, that's approximately where the center would be. So the point at which I could balance the histogram on a point is one way to look for the center of a histogram. Another way that's helpful, I think, to figure out where the center is to imagine that the histogram is a chocolate bar. So the histogram is made totally out of chocolate. If it's in my house, it's going to be made out of dark chocolate because that's my favorite. But I know on that student information survey that I sent out, most of you guys were milk chocolate fans. So we can still be friends, I guess. But you need to come over to the dark side. And so this histogram. It's made out of dark chocolate, okay? And I'm gonna split my chocolate bar with you. So you have to think about where should we make a vertical cut in that chocolate bar so that you and I get the same amount of chocolate, okay? So think about where would you make a vertical cut so that we have the same amount of chocolate in both sides. So those are the two ways I kind of look to help me figure out where is the center of this histogram. So let's practice with these ones that we have right here, starting with this sleep histogram. Okay, where would you guess is the center of the sleep histogram? So you can type your answer in the chat window. Okay, good. So I'm seeing like 6, 7, and yeah, I would probably say 7-ish, somewhere in the middle of this big tall bar since it's pretty symmetric. Or 6.5 maybe, what I would say is the center of that histogram. Okay, looking at the exercise histogram, what do you think is a good value for the center of the exercise histogram? Okay, good, you guys are doing great. So I would say somewhere around 5-ish, somewhere in that range would be a good choice for that one. Sometimes, I don't think any of you guys fell prey to this, but sometimes I have students who kind of ignore the histogram part and they just look at the x-axis down here and they're like, oh, I'm looking for the middle of the x-axis. Well, that would be about 12.5. So I have people that tell me that 12.5 is the center of the histogram. And then I want to find those people and I want to share the chocolate bar with them because I want the left side of the chocolate bar if we're cutting it right there at 12.5. So you can see if I cut it at 12.5, that would definitely not be equal sharing on the chocolate bar. But if I cut it somewhere around 5, then yeah, that would be pretty even for the chocolate bar. Okay, what about GPA? One more. Okay, good. So I think, yeah, 3.5, 3.6. I think that would be a good estimate for GPA. Okay, notice that there isn't necessarily, because we're kind of eyeballing this on a histogram, then we don't need to get like too hung up on like one exact number as being the right number for that histogram. We're getting a general idea. So if I've narrowed it down to like 3.5, 3.6, like that's pretty good. You know, on the exercise, you know, people were saying 4.5, 5, 6, like all of those numbers are good numbers. You know, they're all in the range. So if I was to ask a question like on an exam or something and have you identify the shape, center, and spread of the histogram, then as long as your answer is reasonable, then I would mark it right. So 4, 5, 6 on this exercise one, totally right. If you said 12, I would say wrong. Or if you said 10, I would say wrong. Okay, does that make sense? All right, and then the last thing that we're looking for is spread. How spread out is the data? And the simplest way to look at spread is just, okay, what are the high and the low values? Because that tells you, hey, everybody was between this and this, okay? So for sleep, for example, I could say, okay, you know, all of the data fell between 0 hours of sleep and 12 hours of sleep. So that gives me an idea of how spread out the data was. It went from 0 to 12. If I wanted to, like this exercise histogram, it says, you know, we can see that it goes from 0 to 25. But if I want to be a little bit more specific here, I could say, well, most people exercise between 0 and 10, and then there was a few people that exercised between 10 and 25. That gives me a little bit more information on how the data is distributed, how it varies in that window of 0 to 25. It tells a little bit more of the story because, you know, if you tell people, okay, exercise went from 0 to 25, that does tell you, hey, there's people that didn't exercise at all, and then there was like people who exercised like crazy. But it helps to know, hey, most people exercised less than 10 hours per week. So for this GPA one, you know, then for the spread, I would just say, looks like it went from 2.6 up to 4.0. Or something like that. So spread, like I said, the most basic way you can describe spread is just look at the high and low values. And then if you want to get a little bit more detailed about what's going on in between those two values, you can do that also. All right, there is a special kind of symmetric that we give a special name to, and it's what we call bell-shaped symmetric. And something is bell-shaped symmetric if you kind of smoothed it out, if it looks like a bell. So both of these distributions here are bell-shaped symmetric. And the sleep distribution was also bell-shaped symmetric. And the reason why we're specifically looking for bell-shaped symmetric distributions is that they're going to have some special properties that we're going to talk about that only apply to bell-shaped symmetric distributions. So if it's symmetric, we're also going to take it one step further and say, okay, is it bell-shaped symmetric? So if it's bell-shaped, then like this, then it will also be symmetric. So bell-shaped means symmetric, but it is possible to have symmetric distributions that are not bell-shaped. So for example, I could have something like this. Okay, so this is a symmetric distribution. If I drew a line down the middle, it's a basic mirror image on both sides, but it's not a bell-shaped symmetric distribution. I could also have something that has, you know, kind of two modes to it, two peaks. Again, this one's symmetric, but it's not bell-shaped symmetric. So that's the difference there. So symmetric is great, but bell-shaped symmetric distributions are going to have some special properties in our class. Okay, what do you think is the shape of this distribution, of this dot plot? Okay, perfect, skewed right. Okay, so skewed right because we have kind of the couple people out here, somebody with 8 pets. That's a lot of pets to take care of. So they're a little bit of an outlier out there. And the bulk of the people over here had 0 to 2 pets. So good. Okay, where would you say is a good center? What would you estimate for a good center for this distribution? Okay, good. I would probably say somewhere around 2 would be a good center for that. Again, if I was trying to maybe balance this on a point, maybe I could balance it at 2. And then how spread out was this distribution? Remember, when you're thinking about spread, like don't overthink it. Just think, okay, well, what was the highest and lowest values? Where was the range of values? Yeah, good. Basically, we see them go from 0 to 8. So people had anywhere from 0 all the way up to 8 pets. Okay, and here's just kind of looking for outliers, in case you're wondering what those outliers were over here. Harry Potter, Transformers, and Pirates of the Caribbean were the big moneymakers in 2011. Okay, so here I just want to kind of compare and contrast histograms versus bar charts, because students often get these confused because they're both graphs and they both have bars on them. So it can be really tempting to call a histogram a bar chart because, like I said, it's a graph, it has bars on it. But when we're talking about a bar chart in statistics, we're very specifically referring to a bar chart for categorical data. And then if we're using a chart that has bars on it, then we're talking, that's for quantitative data, then we call it a histogram. So here's 2 different graphs. The bottom one is a bar chart that is movie genre for those movies from 2011. And then the top one is the Rotten Tomatoes score that it got. So this is a quantitative variable versus categorical variable. So we're going to compare and contrast these two. We're going to kind of make a little histogram versus bar chart here. Okay, so the first thing, like I just mentioned, is that bar charts are for categorical data and histograms are for quantitative data. So that's the first thing you're going to put on your comparison chart. All right, the next thing that we're going to look at is the x-axis. So if I look at the x-axis on a bar chart, then you can see that it's the category labels. So we have action, adventure, animation, comedy, etc. down there. And if I look at the x-axis on a histogram, it's going to be a number line. So for a bar chart, the x-axis is categories, and for a histogram, the x-axis is numeric. All right, the next thing that we're gonna compare contrast is the order of the bars. Okay, so looking at my bar chart down here, how was the order of these bars determined? Can you tell by looking at those category labels how they organized the order of the bars? Yeah, alphabetical order, okay? Did they have to be in alphabetical order? No, okay, remember on a bar chart, we're just looking for what are the categories and how do the frequencies relate. So if I were to change up the order of these bars, so instead of going for the OCD alphabetical order method, maybe I'm just gonna switch them all up and just in any kind of order, okay? Would I still be able to tell what the categories were and which one had the most, which one had the least? Yeah, so the order on a bar chart can change, but if I look at my histogram, can I go change in the orders of the bars up here? No, the order of the bars is really important on a histogram, right? We're going from 0 to 100. You can't change the order of the bars or mix them up. That would distort the interpretation of the data. So the order of the bars can be changed on a bar chart, and on a histogram, they cannot be changed. And then the last thing that we're going to compare here is the number of bars. So if I look at my bar chart, the number of bars is just determined by the number of categories. So in this case, we had action, adventure, animation, comedy. So whatever the number of levels are for that categorical variable is, that's exactly how many bars that we're going to have. So it's fixed. It's based on the number of categories. But on my histogram, the number of bars is determined by my bin size, and the bin size we can choose. So in this graph, you can see that the bin size went from 0 to 10, 10 to 20, 20 to 30, 30 to 40, but it didn't have to be that way. I could have made a bin that went 0 to 20, 20 to 40, 40 to 60, 60 to 80, and if I did that, it would change the number of bars, and we saw that with the little slider thing inside of stat keys. So on a bar chart, the number of bars is fixed. It's the same as the number of categories. And on a histogram, the number of bars can be changed depending on the bin size. Okay, so all of this is just to kind of emphasize that histograms and bar charts are different. So make sure when you're answering for what the appropriate graph would be or something like that, that you know which one you're talking about. Categorical data, you're going to be doing a bar chart. Histogram is for quantitative data. All right, so dot plots and histograms are the two graphs we're going to talk about so far for one quantitative variable. Next, we're going to talk about descriptive statistics or numerical summaries for one quantitative variable. And we're going to start with measures of center. Okay, so now we're talking about numerical summaries for one quantitative variable. And first, we're going to talk about measures of center. Okay, and there's two measures of center that we're going to talk about. The first one is called the mean. Okay, and the mean is just what you guys know as the average. So the mean is the arithmetic average. So to find the mean, we're just going to add up all the observations and divide by the total number. So we just take all the numbers, add them together, divide by the total number of observations. That's going to be the mean. When we're talking about notation, the notation for the sample mean is what we call X bar. I'm going to write it down in a second, but I'm going to type out this part first. And the notation for the population mean is going to be the Greek letter mu. All right, so for the sample mean, X bar looks like this. It's an X with a line on the top. And when we pronounce it, we just call it X bar, basically. And for the population mean, it looks like this. We're going to have mu. It's a Greek letter. So it's pronounced mu, like, I don't know, like a cow, like what a cow and a cat would say mixed together, something like that. So it's this Greek letter here. And if we're talking about a formula for the mean, okay, then we would say X bar is equal to the sum of all the individual observations divided by the total number of observations. So this is the formula for the mean. If the formula confuses you, just remember you just add them all up and divide by the total. This little funky E looking thing here is a summation sign, and it means add them all up. And what we're adding is over here all the X values. So each X value, X1, X2, X3, would be a different value in our data set. So we're going to add those all together and divide by n, which is the total number of observations. All right, so thinking back to our data set, I'm going to write down the data up here. Okay, we're going to find the mean number of pets for the sample from our class. Okay, so these were all the numbers of pets people have. So if I want to figure out X bar, the mean for that little sample from our class, I'm going to add up all those numbers and divide by the total number. So there's 13 people in there. So go ahead on your calculator, and I'll do it on mine too. Let's add up all those numbers and see what we get. All right, so, okay, good. So when you guys add it up, you got 33, that's what I got too. Okay, so I take 33 divided by 13, and I get 2.54 if I round to 2 decimal places. So 2.54. Okay, sometimes people are concerned when they see a mean that is not a whole number for something like this when we're talking about pets, because they're like, how can that be the mean? Because you don't know anybody that has 0.54 of a pet. You know, you can't have like 3/4 of a pet. You either have to have the whole pet or no pet at all. It's okay for the mean not to be a whole number. It's fine because we're averaging together. We're saying on average, this is what people have, but we're not saying that every single person has 2.54 pets. Okay, so here's my mean, and that's our first measure of center. Okay, looking at the mean here, what would happen to my mean if we let Crazy Cat Lady into our class? Let's say Crazy Cat Lady has 30 cats, okay? So now if we added a 30 onto there, and then we calculated to the mean, how would that affect my mean? Yeah, it would really increase it, right? It would make my mean be a lot bigger than what it would. Would it accurately represent our class if Crazy Cat Lady was here and she's throwing off our mean number? It would make it look like we all have way more pets than what we actually have. So the mean is what we say it is not resistant, meaning that it's not resistant to the effect of outliers. Okay, so the mean is not resistant. It is going to be affected by outliers. The mean is not resistant. Okay, so now let's look at our other measure of center. Okay, so our second measure of center is called the median. So this is number 2 in measures of center, and it's called the median. Okay, and the median is just the middle value of the data set. So to find the median, the first thing we have to do is we have to order the observations from smallest to largest. And then we're just gonna basically, once they're ordered from smallest to largest, you work your way in from both sides till you get to the center. If you have an odd number of observations, then when you get to the center, there's just one number there, and that number would be the median. So if n, the number of observations, is odd, then the median is the middle number. So it's the middle value. If n is even, then when you work your way in from both sides, when you get to the center, there's not just one value there, there's going to be 2 values in the middle. So you have to take the average of the middle 2 values. So if n is even, then the median is the average of the middle 2 numbers. All right, so first thing we have to do though is put our observations in order from smallest to largest. So I'm going to take that pet data that we're looking at, and I'm going to write it down in order from smallest to largest. And if you've already made a dot plot of your data, sometimes it's actually easier to just grab the numbers off the dot plot because they're already put in order for you on that than it is to look at the data values themselves. Okay, so now I'm going to work my way in from both sides. 13 is an odd number, so when I get to the center, there should just be one number there. So I start at the outermost, then I come in one, then I come in another one, I keep coming in till I get to the very center. Oh, here I am. I'm at the very center here, and one number is left in the middle there, and that number is my median. So my median is 2. So this is how I find my median. Now let's imagine crazy cat lady. She is in our class. Okay, she has her 30 cats over here. What would crazy cat lady do to the median? Would our median change with crazy cat lady? So if crazy cat lady was there, then actually the median would be the mean of 2 and 2, so we'd actually end up with the exact same thing too. So the median is resistant, meaning not as affected by outliers. So even, you know, even if this didn't happen to be the exact same number, it would only affect it just a little bit, whereas with the mean, it affected it a lot. So the median is resistant. All right, so looking at these two measures that we have here, we have the mean and we have the median. They're both measures of center. We want to figure out, okay, well, which one should we use? You know, I have this set of data. I need to know the center of it. Should I use the mean? Should I use the median? And it really is just going to depend on whether your data is symmetric or skewed, whether or not it has any of those outliers. So because the median is resistant, then if your data is skewed or has a really large outlier, like it would if we had the crazy cat lady, okay, then we're going to use the median as our measure of center. So if our data is skewed, use the median as the measure of center. Okay, because it's not going to be as affected by those outliers. So it's going to give us a more accurate value for a typical value for our data set. Now, if the data is symmetric or symmetric-ish, then we're going to use the mean. Because we like the mean. The mean uses all the values in its calculation, so that makes it kind of nice. So it seems like it sort of gives us a little bit more information because it's kind of using everything in there. So if the data is symmetric-ish, we're going to use the mean. All right, so a couple more things as far as like the mean versus the median, okay? Thinking about our histogram then, and mean versus median. Remember the mean, because it is affected by outliers, it's going to be pulled to wherever the outliers are. So in a right skewed distribution, the outliers are on the right, the mean is going to be pulled to the right, which means that the mean is going to be larger than the median. So if the data is right skewed, the mean will be larger than the median. And sometimes it's helpful to remember right skewed, mean is to the right. So right to the right of the median. Okay, and on the other way, if the data is left skewed, the mean will be less than the median or smaller than the median. So in other words, the mean will be to the left of the median. Okay, so here's that dot plot again of all that world gross for the movies. We talked about how Harry Potter was this movie that's way over here that made billions of dollars in 2011. It was the highest grossing movie of 2011. If we look here, I mean, there's also, besides Harry Potter, there's the other really big outliers as well. So the mean of this data was $150 million. But the median was $76-ish million. So you can see there's quite a big difference between the mean and the median for this data set because of those giant outliers. And you can see how much those outliers are really pulling things down towards them. When we have really giant outliers like that, Well, first of all, we want to go back to our data set and make sure that they are legitimate and that we didn't accidentally type something in wrong, or, you know, or something went wacky or something like that. If they are legitimate and representative, sometimes we like to look at the data with and without those outliers just to see how much of an effect that they're having on our data. So with Harry Potter, and we can kind of see how much effect it's having. With Harry Potter, the mean was 150. And without Harry Potter, the mean was 141. So you can see it changed quite a bit. And the median with Harry Potter was 76, and without Harry Potter, it was 75. So Harry Potter had less of an effect on the median, and it had a pretty big effect on the mean. So that's why we have to watch out for those outliers. And another reason why we always graph our data first, because when we do the graph, we're going to see those outliers, and then we're going to be like, hey, I got to be careful about that. And we're not just going to like take the mean and run with it and publish that. We're going to be able to make the right choice on how to look at that data.